Welcome back to Math 160. We only have a few pages left of our Unit 7 notes, so we're going to start there. Once we conclude the Unit 7 notes, I will actually continue to record so that we can take a look at any Lumen questions that you might have, okay? I can tackle some Unit 6 problems, and we can also assign some due dates for Unit 7 stuff as well. Abby, I love it. Perfect. Okay, and yes, we can take the rest of the class time to literally answer any questions you might have. I will keep it recording so that any of you can watch it in the future. All right, let's take a look. Let's finish this up. Practice number 13. 25 females were randomly chosen and asked their age. Their shoe print was measured in centimeters. So we're drawing a correlation between age and shoe print. Notice the Pearson correlation. What do you think about that? What do you think that's kind of implying here? When you look at the Pearson correlation, which is 0.314, what are your thoughts? What does the 0.314 imply when you think of the correlation?
That there is no correlation.
It's low for sure. There is a correlation. It's not no correlation because that our correlation isn't zero, but it is low, right? So how would you describe that? Maybe you need to go back to that scale that you had in the beginning of the notes. How would you describe a Pearson correlation of 0.314? Take a look at that scale. Sam says a weak positive correlation. I would agree with that. It seems like it's a weak to moderate positive correlation, more along the side, more along the weak side. That's excellent. It's good to kind of think about these things. Next, as we dissect this visual, look at the line of best fit. And look at how scattered these dots are, these values away from the actual line itself. It really does show that there's a weak correlation just by looking at this image. Notice here the correlation, the coefficient of determination. I'm just going to draw an arrow right here. So this is the coefficient of determination. It's helpful to label these pieces of information so that we feel confident about interpreting what it is that we see. It would be helpful to write this as a weak positive correlation. The next thing that actually would be helpful is to look at the equation. So the equation says shoe print is equal to 28.14 plus 0.05291 times age. Which value represents age? X or Y hat? Shout it out.
X.
Definitely. X represents age, which implies our shoe print represents Y hat. That might be something that is helpful to write out. So I'm going to say that X represents age, Y hat represents the shoe print. Remember, this is predicted shoe print. Predicted. Good. The next thing we could do there are so many pieces that we can put together to help us really be super successful. What does this 28.14 represent? Do you remember? And what is its notation? What does this 28.14 represent?
Slope.
Oh, you're so close. Slope is going to be the one next to age, next to our X value. So this one's, excuse me, this value represents slope. And do you remember the notation for slope?
mx and
Yep, M represents, well, I'm struggling today. M represents slope, but in statistics, what was the notation we used for slope? We didn't use M, we used a different notation. Look back at practice number 12. If you look back at practice number 12, you'll see the notation there.
Change in y over change in x.
It is. It's definitely the change in y and the change of x over the change of x. But there's a letter that is associated with slope, and it has a subscript.
B subscript 0.
Oh my God, that's so close. That is y-intercept.
Oh, okay.
B sub 0 is our y-intercept. B sub 1 represents our slope. Good. So it's going to be helpful to know all of these things and also to get some practice with this. So 28.14, that represents our y-intercept. I'm just going to say B sub 0 represents our y-intercept. And I'm going to make a note that B sub 1 represents our slope. So we want to keep those ideas organized as we dissect each of the problems. I would totally recommend that to all of you. As you look at your mini tab printouts, you write all this information down, write all over it, right? You're dissecting this, use success strategies. All right, perfect. Now let's get into answering some questions. So what is the slope? Lucy, start us off. We know that the slope is what value? She's like, I am not ready. Leah, start us off. What is our slope?
are you like asking for like the 0.05291 or?
Yeah. Nope, you are correct. Perfect. So we want to look at the exact value this time. With slope, it's going to be really helpful to write it as a fraction. I'm going to try to move this up without, cutting off any of the graph. So we're going to write as a fraction. We know slope is rise over run or fall over run. And then when I write my slope, I also like to give labels. So we know that slope is the change in y over the change in x. And we know that in this case, the change in y refers to the change in shoe print. Change in shoe print. And then that means the 1 refers to the change in age. Modeling this after our last problem from practice 12, if you need to look back just to see how that language was expressed, go for it. Take a look, see how we got. And then I would love for someone to tell me what does it represent in this example. So I would like you to use the appropriate language, which means the labels and the values need to be included. So who can give this a shot? What does it represent? Don't be shy, give this a shot. The sooner we finish, the sooner we could do some review for your questions. Let's go with Ava. Ava, would you give this a shot? What does this represent in the example?
That, hold up, sorry.
Oh, that's okay. Do you see? Can I comment on something? I think what we're doing right now, and I'm pretending to be right next to Ava, is that we're comparing how we used our language for number 12 with this one to try to make that correlation in terms of how we describe what slope is. So yeah, Ava, just go for it. Who cares what happens? What do you got?
Okay. So I'm just gonna say for each additional change in shoe prints, the predicted change in age will increase by 0.05291.
Oh man, you are so close. I'm gonna switch that just
I
a
can
tiny
swap
bit. I'm gonna do like a little swap, but I love the fact that you're like, I'm just gonna go for it. So thank you, thank you, thank you.
You're welcome.
Emma did send a message in the chat, which I love, but I do see that Surujini's hand is up as well. So I would love to give Surujini this shot. Go for it. What do you think?
So I think that for each player, as the age increased by 1, the shoe print in the shoe size increased by 0.05291.
Yes, I love it. I love it. I am going to add what Emma says. She says, for each additional year and age, a predicted size of shoe print increases. Yes, I love all of this. And it's really important to include that value. So Surujini, thank you for putting in that 0.05291. And same, Ava, when you described it, you were sure to include those numerical values. And I think that's really, really important. So let me show you how I would describe this. Consider that X is your independent variable, right? This is the one that is our predictor variable. That might help, you know, I'm going to write this here. This is our predictor variable. Right? It's our input. So the shoe print, this is our response variable. So depending on the age, the shoe print should change. So according to our slope, it says for every additional year in age, the predicted shoe size increases, and this is where we include the value, it increases by 0.05291. And if you're unsure as to the units, remember that at the beginning of this problem, we're told that their shoe print for the 25 females that were randomly chosen, their shoe print was measured in centimeters. So 0.05291 centimeters. Very nice. Slope, I think, is the hardest one to really dissect. It takes a little bit of time and a little bit of practice. But I think the more you do it, the better you get. And also, you want to make sure to review each of the questions we're doing to look at how we're writing it out so that you are consistent as well. Excellent. Thank you so much. I love this. Stephanie, what is the y-intercept in this case? And would you please present that to me as an ordered pair?
Isn't that the 28.14?
It is. So how would I write that as an ordered pair if it's a y-intercept?
Wouldn't you put a 0 in the x place?
Yes, you would. Nicely done. That's exactly correct. When Stephanie is visualizing the y-intercept, she's going to the graph and she's saying, well, if this line continued towards the left and it actually touched this y-axis, it would hit here at 0, and then we're given the value 28.14. So we see the relationship. So yes, we want to write that as an ordered pair. Perfect. Think about what the X value represents, which is age, and the Y value, what this represents, which is predicted shoe print. May I have a volunteer tell me, what does this y-intercept state? What does this mean? I would love for someone who hasn't done this yet.
You mind if I go?
I don't mind at all. Go for it. And Lucy, I do have my spotlight on. So if you click view, click speaker view, and then you'll be able to see just mine. But yeah, go for it, Nick. I'd love it.
Okay, so I was kind of thinking, I haven't written it down yet, so it's gonna kind of come out weird.
We'll go for it. That's how it always starts. Even for me, I'm always like, what can I throw out there?
At the age of 0, the predicted shoe print is already 28.14
Yes, centimeters. What do you think? Of
centimeters.
that?
Yeah.
Is
What?
that meaningful? What do you think of that statement? Is that meaningful to you?
I would say
No.
yes. I would say yes for this problem.
Okay, okay. Argue with him. Someone else, argue with him.
I would say no, because if someone's 0, as in like they're not born yet, they wouldn't have a shoe print, but they could also, like when they're born, they would have a shoe print. But I think that's longer than babies usually are when they're born.
Yes.
Or no, is it?
Yes. Yes.
Okay, I thought so.
Definitely is. Good. Good. I like the dissection of this. In one hand, we're like, a person doesn't exist. Maybe that's what the 0 means, possibly, right? Or they are just born. And then we're thinking, is it possible to have a shoe print size of 28.14? What
I
this
thought
is.
actually, no, never mind. I lied.
Okay, no, but I love how you were like, all right, let's go for it. Let's dissect what this ordered pair means. And then we take that a step further and we say, well, is this possible? So what does this represent? Okay. This represents someone who is, I'm going to write just born, if that's okay. So I'm going to say 0 years old, and then I'll write just born. So this represents someone who is 0 years old or just born with a shoe print size of 28.14 centimeters. We're going to say this is not meaningful. And then we can actually say, since 0 is not in our domain, when you think about this, look at the ages of the 25 females that were asked to contribute their shoe size. They run from maybe 19 all the way to almost 68 years old. So 0 is definitely not in our domain. This is very specific to women in this age range. So we will say this is not meaningful, since 0 is not in our domain. I know you're probably thinking, can't I just say it doesn't make sense because the data collected is for adult women? Sure, you can say that too. You don't technically have to state this is not meaningful since 0 is not in our domain. If you want to be a little bit more intentional with your language and to describe the situation, why it doesn't make sense, I'm cool with that too.
I have a question.
Yeah.
So I know I should have known this domain and range, but just to remind, how do we know where to look for the domain, just in case, for like double check?
Really, really, really good question. I'm going to write something at the very top of this. Let me squeeze this. Okay. So domain refers to all of your X values, where your range refers to all of your Y values. So if we were discussing domain, I would look at what's happening here. I would say, okay, well, my domain refers to my age. And then if we look at all the data that was collected, I've got as low as 19 years old. It seems like this value is like 19, all the way up to, seems like 68 years old or so, 67, 68. Good. Excellent.
I have a question.
Yes, go for it, Donna.
Sorry, I still don't get it. Like, where are we getting the 0 from?
The 0, you mean for the y-intercept?
Yeah.
Oh, the y-intercept will always and forever be expressed as 0, comma, the number.
Okay.
And that's because I want you to visualize something. If I were to continue this line, right? If I were to follow this line of best fit until it hits the y-axis, it's going to hit at exactly here, which is, according to the equation, the ordered pair 0, comma, 28.14. The y-intercept will always be 0, comma, the number.
The Y or the X?
It has to be the y-intercept. The x-intercept, we don't have an x-intercept. We would have to literally follow the graph all the way until it actually hits the x in the x-axis. And we're not worried about the x-intercept in this case because the equation itself gives us the y-intercept and the slope. If it helps, right here above the y-intercept, I want you to write 0, comma, b sub 0. So that way you know every time you write the y-intercept, it's going to be an ordered pair. It's a point on a graph. Go for it.
So back to domain and range, and I know this is going to be a little bit off track. Wouldn't you have to include, like in this problem, wouldn't you have to include it in brackets? Because in brackets it includes like the actual the whole number, and then
Oh,
parentheses it excludes it. So once you have to do that,
this
if
is
we were to do it.
that's a great question. This is not an interval.
No, not the y-intercept. I didn't mean it like that. I meant
Oh, my
like
bad.
just in general. I meant that more generalized.
Oh, yeah, okay. So if you ever are asked to define the domain and range, you're totally right. You would end up using, more often than not, interval notation to denote that. And as long as there are no holes in your line, there are no disjointed points in your line, then you would use brackets because you're including those values. So yeah, you're totally right. I don't think we'll do that in this class in terms of writing domain or range in interval notation. However, we do use that when we talk about range rule of thumb or confidence intervals. We are going to use interval notation for that. So yeah.
Okay.
Yeah.
All right.
I love it. Great. Very nice. I love how we're like piecing all of these ideas together. Good. Good. So yes, as a reminder, Donna, whenever you write your y-intercept, it's always has to be 0. That's your x coordinate, comma, the y coordinate. This is the only way that point will actually sit on the y-axis, right? As if your x is a 0 value. Does that help? Kind of breaking it down like that?
Yes, thank you.
Very welcome. You're very welcome. So check out part C. Why is the equation not a good predictor of the size of a female's shoe print? I'm actually going to give you an idea. Like I'm going to write the explanation here, and I would really love for you to maybe highlight this or draw stars next to it, or just remember that this is the place where we talk about why an equation is not a good predictor, because you're going to need this for your next assignment. So here's how we know that this equation is not a good predictor. According to our coefficient of determination, we finally get to use that value in our description. So according to our coefficient of determination, R squared, right? It's our Pearson correlation coefficient. When we scroll up, by the way, go back to the graph, your coefficient of determination is here. It's only 9.9%. Let me explain all of that. So according to our coefficient of determination, only 9.9% of the variation in shoe size, remember shoe size is our y value. And if it helps, I'm just going to write y because I want you to make that connection. Only 9.9% of the variation in shoe size is explained by the age. Only 9.9%. That's it, which is absurd. So what that's telling us is if you take 100% and you subtract 9.9, you're going to get 90.1. So check this following statement out. About 90.1% is explained by other factors. That is outrageous. So a researcher decided to collect the shoe print size for 25 females, trying to see if there's a correlation. The Pearson correlation was 0.314. We know it's a weak positive correlation. We look at the coefficient of determination and holy crap. Only 9.9% of the variation in shoe size is explained by age. 90.1% is explained by other factors. We don't know what those other factors are. I mean, we can guess, but they're explained by other factors, which means this was definitely a weak study. This was definitely a weak study. Good. Any questions on what we've done for practice number 13? Again, don't forget you have this written out. So if you ever saw a question like this in the future, you'd be like, oh, page 17, let me go back here and let me see how we wrote it out so that I can model my answer based on this result here. Good, turn the page. Practice number 14. Charlie is looking at this graph to determine how much he can expect to receive when he trades in his car. Okay, check this out. Your x-axis refers to the age of the vehicle. Your price, the price tag, right, for the vehicle itself. Notice you are given your equation. It's expressed a little bit different here. And the reason we wanted to do this as we developed our notes is to show you all the possible different variations of your printout. Okay. So above price or wherever you can squeeze this in, we're going to write y hat. And above age, we're going to write x. Give me the value of your slope. Shout it out. Your slope is?
Is it 78.50?
Oh, the slope is not the value.
it?
It's the 485.
Yeah, it's
Yeah.
that negative 485. That's really, really important. I'm going to write out y hat is equal to b1 minus, nope, let's try it again. b0 minus b1 x. So we know that our slope is negative 485. There's not a lot of room, but I definitely want to write this out. So your slope is a negative 485. And we can write that over a 1 in this case, if your heart desires. I mean, we might as well, just so that we actually have that value laid out. And then we actually want to write out our y-intercept. And we'll write that as an ordered pair. So if my slope is negative 485, my y-intercept is going to be the 7850, but we always write it as an ordered pair, 0, 7850. Is everyone okay with that so far? It's going to be helpful if you kind of jot all that stuff down. Notice I'm going to highlight the r squared value. Check it out. Your coefficient of determination is 88.4%. That's pretty awesome. That is pretty awesome. Okay, let's start this off. We're going to identify the predictor or explanatory variable and the response variable. All right, I'm going to call on you randomly to see how you're doing with this. Jenny, what is our predictor variable in this case?
Would it be the age?
Absolutely, which means our response variable is
Price.
exactly the predictor or explanatory variable is age. The response variable is price. Good. Looking at the regression equation, what is the slope and what does it mean in this example? We know what the slope is, so I'm going to write out the slope is negative 485 over 1. Remember that slope, and I'm going to write this out here. In this case, remember that slope is the change in y over the change in x. The change in y in this case refers to price. The change in x refers to age. I want you to think about this for a moment. Charlie is looking at the graph to determine how much he can expect to receive when he trades in his car. Angelica, what do you think this slope is telling us? What do you think that slope is saying to us? What's happening? What can you expect when Charlie trades in his car?
Is that how much he would get for 1-year-old car?
Maybe. It's not an ordered pair, so something's happening as time goes
Is
on.
that like the depreciation rate each
Yes.
year would be?
Yes, perfect. So Angelica was like, wait a second, this is like depreciation. What's happening is that for every increase in 1 year of age, the car is predicted to decrease in value. That's that depreciation. The car is predicted to decrease in value by $485, and that's every single year. So let's write that down. For every additional year in age, the car's value is predicted to decrease by $485. For every additional year in age, the car's value is predicted to decrease. Wow, I can't. There we go. It needed an E. To decrease by $485. Excellent. Very nice. We'll go with Pi. Pi, what is your y-intercept from the regression equation? And then what does it mean? So would you remind us, what is the y-intercept in this case? She may have stepped away from her computer. Ooh,
Hi, Professor.
hi.
So the y-intercept is 0. Give me 1 second, please.
Yeah, go for it. And while she is thinking about what the y-intercept is, we should all be thinking about interpreting what this y-intercept says.
Is it the 7850?
Yes, perfect. 0, 7850. Remember the strategies. Thank you, Pi. Remember the strategies you would use for this? Label what the X is. We know that X is age. Label what Y is. We know that this is price. Good. So let's go with Holly. What does this ordered pair 0, 7850 mean to us? What does that mean?
That would mean when the age of the car is 0, the cost would be $785.50. I mean 7,850.
Yes, perfect. And so if a car is 0 years old, what does that tell us? That the car is
It's new.
brand spanking new. Good, let's write that out. So when the car is 0 years old, AKA brand new, Charlie can expect to trade in his car for $78.50. What do you think? Is that meaningful? Is that, oh yes, I love it. Some of us are like, yes, definitely. I mean, we know this firsthand too, right? If you bought a new car and you left a lot and you tried to sell it, would you ever get the exact same amount that you paid for that brand new car?
Absolutely not.
Hell no. Hell no. You know, the second you leave that lot, it depreciates in value like something insane. So yeah, this definitely makes sense. So let's write this is meaningful. Crazy, right? I think that's such an absurd idea. Whatever, I don't make the rules. Okay, this is definitely meaningful. Cool. Let's look at part D. You're going to need the graph, so you may want to just like hold on to this page so you can flip back and forth. So part D asks us to interpret what R-SQ means in this example. So look back at your graph and let's go with Grace. What is the value of R-SQ for this particular problem? What do you think, Grace?
88.4.
Aha, okay, wait a second. 88.4%. What is this particular notation mean? What does it represent?
Is it the coefficient of determination?
Absolutely. Coefficient, nicely done. Coefficient of determination. Remember, this is our R squared value. R squared, you see it? Haha. Make that connection, good. Okay, so I'm gonna state the interpretation again, if that's okay. So this says approximately 88.4% of the variation in price can be explained by the age of the car. Take 100, subtract 88.4, and we can say
11.6%.
Yes, 11.6%. So we can say about 11.6% is explained by other factors. Not bad. That's a really, really strong correlation. I like the fact that our coefficient of determination is so high because it's really kind of hinting at the fact that this is a powerful relationship here, that these are definitely correlated. Sarojini, will the R squared always be given? I would say that with most regression plots, you will see an R squared value. If you don't, you can always calculate the Pearson correlation coefficient. And if you know that one, you can easily find the coefficient of determination because you take R and you square it. So in which case, it's a perfect time for you to ask that, by the way, because look at part E. So based on our R squared value, what is the linear correlation coefficient? So remember, so based on R squared, they want to know what is R. If you know that your R squared is 88.4%, which is the same as 0.884, then to figure out what R is,
You
we're
square
going,
root it.
yes, absolutely, you square root it, beautiful. So R is going to be the square root of 0.884. And we see that it's going to be, when you square root it, what do you get? And give me your answer to 2 places after the decimal.
0.94.
Yes, 0.94. Now there's one thing we have to do. I'm going to make a note. Check the graph to determine if positive or negative. Look at your graph. And I'm going to cover this for a moment. Notice that as age increases, price decreases, which means our Pearson correlation coefficient will be negative. As age increases, price decreases, which means our correlation will be negative. So let's write that out. Our linear correlation coefficient is negative 0.94, since as age increases, price or predicted price, I was going to say predicted trade-in value, but I'm okay with predicted price decreases. If you were to look this up on your scale, this is going to be a very strong negative correlation. So I'm going to write in here, very strong negative correlation. It's almost a -1. It's almost a perfect correlation. That's insane.
Can I just add like a note in
Yeah.
here, because I feel like this would happen to like someone like me.
Go for it.
So, instead of, just like be careful of like not adding a negative in the square root, because then it's gonna end up being an imaginary number called I. It's gonna have like the number I in it. So just like be careful of that. It's not a real number, so don't do that.
Yes, good point. So even if you're thinking that your correlation coefficient will be negative, Nick's totally right. You don't want to put the negative inside underneath the radical, because first off, let me show you what will happen. So if we take the square root of negative 0.884, you're going to see, nope, that's not happening. And that's because it would be an imaginary number. So keep that negative as your descriptor of your correlation coefficient for after the fact. So once you find the value, now check the graph to determine if it's going to be positive or negative. Okay.
Just something that I learned in like pre-calc
Yes.
when I did pre-calc in high school. So
Yes.
yeah.
Yes. Absolutely. I love it. Absolutely. Good
I have a
call.
quick question.
Yeah.
How'd you get the 11.6?
Oh, let's see, right up here. What
Yeah.
we did was, because 88.4% of the variation in price can be explained by age, then you say, well, what percentage is left, right, out of 100? So if 88.4 is explained, then 11.6 is explained by other factors outside of the price or outside of the age. Good.
Thank you.
You're very welcome. You're very, very welcome. Part F asks us, why is this equation a good predictor for the trade-in value of the car? So essentially it's the same reasoning as part D, but I'm going to write out what you should have here. So the coefficient of determination is fairly high. And explains 88.4% of the variation. With only 11.6% being explained by other factors. That's really, really massive. But in addition to that, we also know that we have a very strong negative linear correlation coefficient. Good. Good. The coefficient of determination is fairly high and explains 88.4% of the variation, with only 11.6% being explained by other factors. We also know that we have a very strong negative linear correlation coefficient.
Feels
Cool.
like an English class right now.
I know. That is, I mean, statistics is really all about not just the calculations, but your interpretation. Those two things go hand in hand all the time. There is some pretty sophisticated stuff out there for sure. And yeah, it does feel like you're writing for forever. What are the limitations for this equation? Here are the limitations. This is another one I would love for you to highlight, because you're going to be asked this question both on your regression assignment and also your final exam. So what are the limitations? I'm going to list them for you. Your first limitation is that we can only make predictions within the time frame from which this data was taken. Right? We're thinking about, we can make predictions on the trade-in value of the car, but it has to be from the same time frame because that's where we collected our data. It's not going to be meaningful if, let's say, this were taken in 1970 and we're like, hey, what's going to happen in 2030? No, there's no way that this is going to be applicable to the different time frame. Your second one is we can only make predictions within our domain. So when you think about your particular graph here, it has to be within that specific domain pertaining to the trade-in value of the car, which means, so for instance, if you were looking at, oh, what's the trade-in value when the car is 20 years old? that is going to be outside of the domain. And you'll know that because you can actually find out how long it takes before that car's trade-in value will be worth nothing. And it's definitely before the age of 20. And then of course, your third limitation is we can only make a prediction for the population from where this sample originated. Okay. We can only make a prediction for the population from where this sample originated. Good. All I have to do now is read to you one more practice problem. I mean, not really a practice problem, it's a Khan Academy. So I just want to read that to you, and then the limitations of the line of best fit, which again, we're going to highlight like crazy. And then we are done with unit 7. So let's check this out. There's another Khan Academy activity. Try this out. Click on this link, check it out, see how comfortable you are with looking at interpreting slopes and y-intercepts, especially if you're like, ooh, I need a little bit more practice on that. Play around with Khan Academy. And then last but not least, limitations of the line of best fit. This is really important. If you're ever like, what do you mean by limitations? I'm going to say page 20. Okay. The regression equation should be used to make predictions only about the population from which a sample was drawn. The regression equation should be used only to cover the sample domain on the input variable. You can estimate values outside the domain interval, but use caution and use values close to the domain interval. Kind of like when we talked about the shoe print, was the y-intercept 0, 28.14 meaningful? No, because this is not going to be applicable to newborns. So no. C, use current data. A sample taken in 1987 should not be used to make predictions in 2020. And then lastly, the equation should only be used if the graph of the regression line on the scatter plot fits reasonably well. And the linear correlation coefficient R indicates there is a linear correlation. If that's not happening, then it's a weak study, right? Like the shoe print with age. So you're not going to use that to make predictions because it's not a very strong predictor. Excellent work, everyone. That was fantastic. That concludes Unit 7. So at this point, I am now ready to answer any questions you have from Lumen. I know that there are some questions on Unit 6, but if you don't need any help, you are free to go. The Unit 6 homework was extended. Oh, before you leave, I spoke too soon. The Unit 6 was extended. Let me go to that. We need to go to our course. So you see the homework is due this Sunday, which is the same as your next test. Don't forget this, okay? You do have 3 attempts here.
I thought it was due today. That I kind of looked at it yesterday and I was like, huh, she switched it. So I kind of got nervous at first and I was like, oh my God, is tomorrow the 21st?
Sorry for freaking you out. No, I gave an extension so that everyone can have extra time. But okay. Speaking of, let's come up with a due date for correlation and regression. As you know, next week, we only meet one day because we have off Wednesday, Thursday, and Friday of next week for Thanksgiving. Yeah, my uncle says happy Thanksgiving. He's the most ridiculous person, but that's how my grandmother with her thick Spanish accent always sounded like she said happy Thanksgiving. But anyways, okay. So I know it's so dumb and I love it. So we're off Wednesday, Thursday, Friday, which means we only meet Monday. I will be recording one session for you. I know, I'm so sorry, but I want to make up for a previous class session. Okay, so don't be alarmed when you see 2 videos posted instead of just the 1 from our class session. So having said that, let's
December
come up-
1st.
December 1st. Are we in agreement on December 1st?
Yes.
Yeah.
Yeah.
Everyone's like, yeah, that works.
Was
Okay,
our-
we'll do,
Is our test on Sunday? Does that include unit 7 as well?
no. This one Sunday, I'm pushing
Oh,
7.
just 1 through 6. Oh my god, I was worried because I was like, oh my god, it's on 7 too.
No, you'll have plenty of time. I do not want to assign this due on the 1st. I actually am going to push that to Sunday, okay? Because it's a Wednesday, middle of the week. Everyone should have at least the weekend to finish this assignment. So the 5th will be when your application problem is due. Okay, everyone, are we cool with that?
Yes.
Thank you.
Okay. You're very, very welcome. All right, having
Thank
said
you.
that, those of you who want to stay, please stay. Everyone else, I will see you on Monday. Have a great
I have
day.
a question for unit 6.
Yeah,
The first one.
normal distribution basics, beautiful.
The question is 13. Like, I just need help with the first part, and then maybe I'll get the second part.
Yeah,
But I was so confused.
no, that's
Like, I kept getting the wrong one. Like, I kept getting like 2 below, and I was like, what is going on?
okay, which might be okay, by the way. So yeah, let's just see what's going on.
So
So
it wasn't like a small amount. It was like,
oh, you're like, this cannot be. So the systolic blood pressure of adults in the USA is nearly normally distributed. By the way, what I'm going to do is I'm going to write out information on a scrap sheet of paper because it's going to be a little bit harder to write on our Lumen. So we're told it's normally
Question?
distributed with a mean. Yes.
Quick question. So with that homework, it's saying that it's not completely due. Is that because you withdrew that one question?
I withdrew 18.
18,
Yes.
yeah. So
So
it's saying everything else, I'm good?
yeah. Oh yeah.
Okay. All
Yeah,
right. Thank you so much.
You're welcome. Perfect. So with a mean of 117 and a standard deviation, sigma of 25. So I'm taking notes as I'm doing this. It says someone qualifies as having stage 2 high blood pressure if their systolic blood pressure is 160 or higher. So stage 2 is a BP of 160 or higher. So a BP of greater than or equal to 160. That would be stage 2 high blood pressure. Around what percentage of adults in the USA have stage 2 high blood pressure? Give your answer rounded to 2 decimal places. So what we're going to do in this case is we are going to actually look at the information that we have here, mean, standard deviation, and we know that stage 2 is a blood pressure of 160 or higher. This is going to represent your X. So we're going to use our Z-score formula to figure out where we are on our Z-score, on our normal curve, I should say. So we have Z is equal to X minus the mean divided by the standard deviation. So we're going to go through these steps first to figure out our Z-score. We have Z is equal to X is 160, the mean is 117, and the standard deviation is 25. So let's go ahead and calculate this. 160 minus 117, that's 43. Divide by 25, and we get a Z-score of 1.72. Stop me, please, if I'm going too fast, by the way, okay? The next thing I'm going to do is I'm going to actually draw my normal curve because I like to have the visual accompany what it is that I'm trying to figure out here. I'm going to plot my Z-score of 1.72, so that's approximately here. Now we are told that if a person has a blood pressure greater than 160, then they're in stage 2. So that means if someone falls in this region that I'm highlighting, they have stage 2 high blood pressure. Now, we're going to go to our z-score table. You'll have this from your Unit 6 notes. It's the last 2 pages. And we're going to open up to the positive side, and we're going to look at a z-score of 1.72. So can you tell me?
the answer.
Yes, I love it. Go for it. What is 1.72?
So it is 0.9573.
Yes, that represents the area to the left, 0.9573, over to the left.
Once you subtract 1 from the number to get the area to the right.
Yes, absolutely. So that means the area to the right is going to be 0.0427. Excellent, Donna. So the question is asking us around what percentage of adults in the US have that high blood pressure. So if we know that the area is 0.0427, now let's turn that to a percent. So we're going to say approximately 4.27% of adults. And we'll be able to throw that into Lumen. And look, 4.27%. So that is correct.
Oh, so it wasn't a, because I was thinking that was the z-score, and I was like, why is it so high?
Oh, okay. So that's the other thing too, is as you go through this, do this step by step, calculate the z-score, plot it here, shade the region, and then use the table to find those areas. That way you can say, oh, the area or the probability is 0.0427, which we can then turn into a percent.
So then if you sample 2,000 people, or like the one below it, like would you put the 2,000 as the X?
Actually, no. So X refers to your blood pressure, right? Think about what this is saying. We know that we can expect 4.27% of all adults to have a high blood pressure. But now they're telling you how many adults.
So I have a question too.
Yes.
The 2,000, would that be like your end sample, like how many people you you sampled?
Yes, it is.
Oh, so are you using the sample one? Like the sample?
We actually don't have to use that fancy formula. What we're doing here is, if you know that 4.27% of adults have stage 2 high blood pressure, then we want to know what is 4.27% of 2,000 people.
Oh, so you multiply it?
Yes,
okay.
Exactly.
I'm thinking too far into this.
Turn that into a decimal again, and then multiply by 2,000, so that we can figure out roughly how many people would have stage 2 high blood pressure. And what are you getting for your answer? And anyone can throw it in there.
I got 85.4.
Yes. So we're not going to say 85.4. I would actually say 85 people or 85 adults. So they gave us the number of adults because they want to say, if you know that 4.27% of them have high blood pressure, well, how many would that be if you had 2,000 people? And you're going to say, well, that's 85 people. Good. Next, it says stage 1 high blood pressure is specified as systolic blood pressure between 140 and 160. And then you have to figure out what percentage of adults qualify for stage 1. So the idea here is that you need to figure out the z-score for a blood pressure of 140. We already know the z-score for 160. We need to find the z-score for 140. Okay, so we go through this same process. And we say this time, X is going to be 140. So when the blood pressure is 140, we're going to plug that into our formula and find the z-score.
So it'd be 0.92.
Yes, exactly, 0.92. So if we were to draw this curve again, and we were to plot those points, 0, 1, 2, 3, 0.92 is slightly to the left of 1, of course. Draw the dotted line up. We know that blood pressure of 160 has a z-score of 1.72. That's approximately here. And what they're asking for is, what is the percentage of the population that lies in this region, stage
Oh, so you
1?
would subtract it.
Yes, you would subtract the areas. Yes, exactly. Good, 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 good. Is this starting to make more sense?
Yeah.
Beautiful. So find the area to the left, find the area to the left, subtract, and that'll give you just this sliver, which you can then turn into a percent. The last one, part D, I would like to do this last one with you. It says your doctor tells you you are in the 30th percentile for blood pressure. What is your systolic blood pressure? That means, what is X? So what's happening here is that you have to figure out what is the z-score related to the 30th percentile. So if I were to draw the curve again, I'm basically saying to myself, well, first off, 30th percentile means you outperformed only 30% of the population. We know that if we went to the halfway point, that'd be 50%. So it's somewhere over here. So somewhere over here represents an area of 0.30. And we need to figure out what that z-score is at that point.
I got the z-score. Do you want it?
Oh, damn. Holy crap. Hold on. Let me find it as well, because I don't have it. Let me see. Where are you? Where are you? And
Negative point.
okay, I'm now ready.
53, negative 53.
Negative
Point negative 53 because it's in between.
It is. Is it closer to the one on the right?
I think closer to the one on the left.
Ah. Oh, so it is closer to the one on the left. So the z-score is going to be negative 0.52.
Oh.
Yeah. So negative 0.52. Excellent. We still use the z-score formula, but we know z this time. Z is negative 0.52. What we don't know is the blood pressure. We know the area, or excuse me, we know the mean, we know the standard deviation, and all we have to do is solve. Does that help?
Yeah.
Yes.
Thank you so much.
Excellent, excellent, excellent. Good. Do we have another question we'd like to look at?
Actually,
yes.
Go for it.
She can go ahead, and then I guess I don't know if it's one of mine.
Okay.
It's looking for the 30th percentile. Why do you have to put it in the z-score?
Oh, so the 30th percentile just refers to the percent of the population that lies in this region, which means in order to figure out what that raw data value is, we have to have a z-score. Think about the fact that you have 1, 2, 3, 4 unknowns in your z-score formula. If you don't know X, you better find all the other 3, otherwise you can't solve for it. So that's why it tells us we know the mean, we know the standard deviation, we definitely need to find the associated z-score so that I can then find my raw data value.
Thank you.
You're very welcome.
Have a nice day.
You
I have
too.
a question too.
Can you do 14?
14. So the same unit? This guy? I don't hear anything.
Oh, yes, I
Okay.
don't know why you weren't here.
That's okay. The life of a Radio Shack record player is normally distributed with a mean of 3.3 years and a standard deviation of 0.8 years. Radio Shack guarantees his record players for 2 years. Find the probability that a record player will break down during the guarantee period. So what we're basically saying is, what is the likelihood that this record player will break in fewer than 2 years? So we want the probability of X being less than 2 years. So your formula, you're going to essentially use this same thing. Z is equal to X minus mu over sigma, where we don't know Z. We do know that X is going to be 2. Okay, so we want to see the probability that the player will break down during the guarantee period, which is 2 years or less. So we're going to write 2 minus, the mean is 3.3, and the standard deviation is 0.8. So we're going to go ahead, do 2 minus 3.3 divided by 0.8. That gives us a z-score of negative 1.63. Let me stop my screen share. You're then going to graph this. Now remember, they want to know the probability that it'll break in the guarantee period. So we want the probability that X is less than 2. When we plot this value, we see that negative 1.63 is approximately here. Draw your dotted line up, and they want the probability to the left, which is nice because that's exactly what the table gives you. Sudhajini, does that help?
Yes. So we always have to do this formula first. If we have to find the z-score, we always have to do the formula, get the answer, and then look for it on the curve.
Yes, absolutely. Absolutely.
Okay. And in a case like this, where there's a negative 1.63 is, that's my struggle, the curve and the table. So in a case like this, I would look on my negative side of my table,
yes,
and I would find where negative 1.63 is.
Yes.
Which is 0.5155.
Yes. But then when we look at here, negative, excuse me, 0.05155, when you go to your actual lumen, it's not one of the choices, but it's super close to this one.
Okay.
Okay. So you want to pick the one that it's closest to, especially since you knew that our z-score is negative 1.625. So we see that we're kind of in between those two values. So we want to find the one that's closest.
So always do the formula first and then look for the.
Yes, absolutely. Absolutely.
I was really, I didn't understand this whole.
I think this part especially is a little tricky too, because it doesn't outright say that X is 2, but you have to think about what it's saying to you, right? It's giving you the mean, it's giving you the standard deviation. Immediately my brain would be like z-score, normally distributed z-score, right? All of that screams z-score. And then here, when it says it's guaranteeing its record player for 2 years, it's the same unit as your mean and as your standard deviation. So this is going to be your X value, right? Your z-score is a standardized score. So it takes your raw data value and it assigns to it a z-score, which is what helps us to interpret what's going on. Good, very nice. Who has the next question?
I do.
All right, Donna.
So my question is, can you please help me? And I know I'm going to sound really stupid, but I would like to know how to do the variance, to find the variance.
Do you have an example problem?
Yes.
Okay, which section and what number?
Oh, it's the exam.
Oh, the exam. Okay, so
no matter how I got the numbers were relatively closer, but like it's just like slightly a little bit. And no matter how many times I tried, I just couldn't get it. And it was frustrating.
I will say that it depends on what you're finding the variance for. So if it's the variance for the binomial distribution, remember the following pieces of information. So if it's a binomial distribution, you know that the mean or your expected value is going to be found by taking n times p, right? And then you know that the standard deviation is found by taking the square root of n times p times q. Now remember the notation for variance and the notation for standard deviation. I think this is going to help you out a lot. We know that the standard deviation, the notation is S, right? For a sample. We know that variance is S squared. So Donna, if you know standard deviation, you know how to turn it into variance.
Okay.
Right?
I think I know how to do that one, but the other one, it was so different.
Okay, okay. I do want to give you some time to try out because it is an exam problem. So I do want to give you some time to try to figure that out. Just remember the relationship between standard deviation and variance.
So the standard deviation, I'm sorry again.
So
you get your mean, which is the sample and then the probability of success, right?
Yes.
You time it together.
Yes.
And then to find the standard deviation, you get n and then the number of success and failure and multiply together and then square root it, which gives you your standard deviation.
Yes.
And then to find the variance is that you square.
Yes.
Square.
Yes.
Yeah.
Exactly. Yeah. So if yours, for whatever reason, let's say your standard deviation was 2.53, your variance is going to be 2.53 squared. So your variance is going to be 6.4009. Like you can always go back and forth like that. Like if you knew the variance, take the square root and that gives you the standard deviation.
Okay. I got it.
Awesome. Perfect. All right. Who's got the next question?
Can you do 9 on the theorem one?
Yes, 9 on the second homework assignment. Let's look at number 9 on sampling distributions, central limit theorem. And here we are. Okay. Engineers must consider the breadths of male heads when designing helmets. The company researchers have determined that the population of potential clientele have head breadths that are normally distributed with a mean, I'm going to write this out, a mean of 6.1 inches and a standard deviation of 1.1 inches. Now it says, in what range would you expect to find the middle 95% of most head breadths? So the first thing we're going to do is we're going to draw the curve. We want the middle 95%. Let me stop my screen share so you can see this clearly. So the middle 95% would be here, right? Which means that 5% is left to be split between the tails. Do you agree with that? Mm-hmm. So if 5% is split between the tails, that means each tail is 2.5%. What we're going to have to do right now is figure out what are those z-scores pertaining to the area to the left of a 2.5%, but the area is 0.025. That's what we're looking for. We want an area of 0.025. So we're going to go to our z-score table. We're going to look at the negative side, and I'm going to find 0.025 as best I can. What is the z-score pertaining to an area to the left of 0.025?
Mine was actually a little different. My question wants us to find the middle 50%.
Okay,
Um,
let's do this one together only because it's the same process.
yeah.
Okay, beautiful. So if you looked at your z-score table, what did you get for an area to the left of 0.025?
Negative 1.96.
Yes. So because this is symmetric, that means your other z-score is a positive 1.96. Perfect. So we find each of our z-scores. And then what we're going to do is we have to figure out what the actual values are for the head breadths, right? For the helmets. So we're going to calculate two different values. We know that z is equal to x minus the mean divided by the standard deviation. So we're going to use this z-score. Negative 1.96 is equal to, we don't know the actual head breadth, so we're going to calculate that. We know the mean and we know the standard deviation. So we're going to go ahead and solve each of those equations where we have a negative 1.96 and we have a positive 1.96. So I'm going to go ahead and I'm going to take the negative 1.96 and multiply it by 1.1. That's going to give me negative 2.156 is equal to x minus 6.1. This is going to be a positive 2.156 is equal to x minus 6.1. I'm now going to add 6.1 to each side. My lower value is 3.944 inches. And my higher value is 8.256 inches. Stop me if I'm moving too fast, okay? If we go back to the actual problem itself, notice that they rounded to the nearest tenths place. So the range would be 3.9 to 8.3. So we rounded to the nearest tenths place. If you were to draw samples of size 43 from the population, in what range would you expect to find the middle 95% of most averages? Now this is where it screams central limit theorem, because now we have an actual sample size, 43. We are now ready to use a different z-score formula. Same idea, because it's still the middle 95%. But this time we have to use the fancy z-score formula. So we're going to use this formula here. Z is equal to x bar minus mu over sigma divided by the square root of n. The really awesome part about this, everyone, is the fact that we already know what the z-scores are that bound the 95 middle, the middle 95%. Oh my gosh, I can't talk. So we already know what those z-scores are. We also know that n in this case is 43. So I'm just going to write n is equal to 43. So we want to find the sample averages using all of this information. Same thing, we're going to start with the negative 1.96. We don't know the mean of the sample. We do know the mean of the population. And we know the sample size. So you see how I plugged in all of those values? Surujini, you have a question?
Yeah, I missed, this is still recording, right?
Yes, yes.
Because I missed when I moved just now, so I can come back and rewatch which one this is.
Yes, absolutely. We are just looking at the second homework assignment, problem 9.
Yeah, I figured that out when you showed it just now.
You're like, it's got
But I missed the first half. And
oh, okay. Yes, yes. It's definitely recorded, so you'll be able to see that for sure. Good. So now that we have these equations set up, if I were you, I would actually calculate the denominator first, that fraction. So 1.1 divided by the square root of 43. That's going to give me a pretty long decimal. Because I want to make sure that I'm as accurate as possible, I'm actually going to write the decimal like this. So we get 0.167748. I'm going to use all of those values, again, because I want to be as accurate as possible. And then I'm going to proceed forward and solve. So 0.167748. And then, of course, we do the math. Is that helping? Does that make more sense?
Yes.
Score. Okay. Once you solve those, you'll then be able to answer the questions. What is the, in what range would you expect to find the middle 95% of most averages for the breaths of male heads in the sample? Okay. So you'll be able to calculate that. Notice for that second problem, they do want your answers to be accurate to 2 decimal places. For the first one, they wanted 1 decimal place, and that's something we can just kind of play around with to make sure. I can certainly edit the code so that it says to 1 place for the first problem and then to 2 decimal places for the second half. Good. Good.
Professor.
Thank you.
You're welcome.
Can I ask the last question?
I think Ho has a question.
Oh, okay.
But then, yes, Donna, go for it. So Ho, what's going on?
Yeah. How did you get negative 1.96 at the beginning?
Oh, we go to the table. So if I know the area to the left is 0.025, we go to the z-score table, and I'm going to share that with you. And I look in the inside of the z-score table, and I see that the area to the left is 0.025 here, and that pertains to a z-score of negative 1.96. Does that help?
Oh, yeah.
Good.
Yeah, I got it.
Perfect. So you always go to the table and you look inside, since these values inside are the area to the left of the z-score. So that's why we say negative 1.96. And then, of course, because it's symmetric, that means the other z-score is going to be a positive 1.96. It's both positive and negative. Good. Donna, you are up.
Okay. So my question again is I just want to know how to do the and because I get confused a lot, how would you do like the gosh, I'm going to like ask it in a different way just because it's a I don't know how many people have already taken their exam here.
Okay.
But can you please like show me how to compute to compute the probability of drawing 2 hearts from a standard deck of 52 cards?
Yeah, sure. The probability, we'll just do the probability of picking 2 diamonds, just to make it a little different. Not that it matters. You're picking 2 diamonds from a standard deck of cards. Do you know whether or not you're putting them back after you pick?
No.
Okay, so you're keeping them. That's what it is
Yes.
implying. So you're going to pick your first card. The chances that you get a diamond are 13 out of 52. And then you're actually going to keep that card. So you put it in your back pocket and you go back to that deck of cards and you're like, well, now how many diamonds do I have?
And
you
then
would say
13 again.
no, it can't be 13 because you've got the
No.
card in your back pocket.
So it's gonna be 12,
Yes, out of how many cards?
51.
Yes, good. And
But
because
we
you wanted-
didn't, but we did not like, we did not keep the card. We put it back, the card. Did you
you
know
just
what I
said
mean?
it didn't, you just told me that they didn't tell you
Uh.
whether or not you put it back, right?
I'm sorry.
No, that's okay. So if the problem doesn't imply, it doesn't say with replacement, then what's
Okay.
happening here is that you're picking two diamonds, one and then the next card, and you are literally holding on to them.
Okay, but if you did say like
With
to
replacement,
replace it will be 13 out of 52.
again, yes, and you would
So
still
my
multiply
question
those.
is to this part right here, would you times it or would you
Yes.
add it?
No, it's not adding. It's
Right.
multiplication because you're picking a diamond and then a diamond. So and
Okay.
implies multiplication, where
Mhm.
or implies addition.
So I think what I came confused, I did times the 13 times 13, but the 52 I did not because it's same. So I was like, okay, if the denominator is same, then I don't have to.
Remember, there's a difference between this and this. See?
Okay,
Good. Be very careful with that.
I got it now.
You're welcome. Any last question, Emma?
I have a question. It's on part 2 of Unit 6 homework.
Yeah, okay.
My question is for number 5, and then I was wondering if 6 and 7 were similar because I'm also confused on those.
Okay, so with 5, notice that you're given the mean and the standard deviation, and you're also given a sample size. The first one says, find the probability that a single randomly selected value is greater than 59. So Emma, are you going to use the central limit theorem z-score or the traditional z-score formula?
Is it the traditional?
Yes, good. So for this first part, x is 59.
Mm-hmm.
So you're going to calculate the z-score when x is 59, and you know the mean, you know the standard deviation. So you're going to use that to find the probability. Keep in mind that it says the probability that x is greater than 59. So which region would you shade, to the left or to the right?
To the right.
Yes, but the table only gives you the area to the left.
Mm-hmm.
And you know how to get the area to the right, correct?
Yeah.
Beautiful. So that's that first part.
Okay.
This second part, look at how it's worded. Find the probability that a sample size n equals 21 is randomly selected with a mean greater than 59. For this particular part, you're going to use your central limit theorem. You're going to use the z-score for that one, which is the sample mean minus the population mean divided by the population standard deviation divided by square root of n. You're going to use this big formula for this part where your sample mean, that M capitalized, that means sample mean, is going to be 59.
Okay.
Okay, and then just keep in mind, it'll be 59 minus 40 divided by, and then in the numerator, it's 79.1 over the square root of 21. So just be careful as you calculate that. But that's it. They just want you to use the z-score formulas for each.
Okay. And with the mean, would we put a number in for there, or we're finding the z-score?
You're finding the z-score for each of these. So notice for the first one, you're given x, and for the second one, you're given the sample mean, x bar.
Okay.
So the capital M is the same as sample mean.
Okay.
Good. Good.
And then 6 and 7, are they similar?
Yep. Yes.
Okay.
You're
Can we
given
go
the
over one
sample
of
mean here.
Okay.
Good. Keep in mind that the language will tell you which region to shade. So if they want to find the probability that the mean length is greater than 16.8, once you find that z-score, shade the region to the right, because that's what you're looking for.
Okay.
Good. Yep, 7 is exactly the same.
Okay. Thank you.
You're welcome. Actually, with 7, you're told the probability this time, so you have to find the z-score. I'll show you this one real quick. just so that you don't feel lost, because the other two were similar to what we were just doing. So for number 7, you're given the mean is 223 grams, and you're given the standard deviation is 15 grams, and you're told that N is 5 fruits. So you want to figure out, if you pick 5 fruits at random, then 9% of the time their mean weight will be greater than how many grams. So we want to look at our normal curve, and we want to do the same idea we did before with figuring out that 9% of the time. So we're going to notice that the area to the left of a certain value is 9%, which we know is going to be in this tail. 9% is the same as 0.09. So we want to find the z-score pertaining to an area to the left of 0.09. So I'm going to look at the negative side of my standard normal distribution table, my z-score table, and let's look for 0.09. I think I found it. So let me share my screen with you just so you can see exactly what I'm doing here. Oops. I almost canceled the meeting. Ha. Okay, so take a look at my z-score table. 0.09 is in between these two values. We just have to figure out which one it's closest to. I'm going to check the one on the right. Oops. 851, got it. And that's 0.00149. Okay, it's closer to the one on the left. So it's closer to this value, which is negative 1.34, negative 1.34. So now, Emma, because we have that z-score, which is negative 1.34, we're now able to use all of that information in our formula. So we have z is equal to, we don't know what that value is for x bar, but we do know that the sample, or the population mean is 223. We know the population standard deviation is 15, and we know that N is 5. And then you'll want to go ahead and solve this value. Okay.
Okay, thank you.
You're very, very welcome. Good. Surujni, last question.
The first set of homework, number 9.
First set of homework, number 9. Let's take a look. All right. A quick survey of peanut butter prices has a standard deviation and a mean of 0.26 and 3.68 respectively. We want to find the area for a peanut butter jar costing less than $3.50. All right, Surujini, talk me through this. What information do you know?
The mean is 0.26. The standard deviation is 3.68.
Switch them.
Oh wait, yeah, yes.
Good.
I realize, yeah.
So 3.68, standard deviation is 0.26. Tell me more.
And would this be the end, the 3.50? Would it be the end? We want to know how much costs less than $3.50. Would that be the end?
Okay, N represents the number of peanut butter jars. So N would be the sample size, right? Like how big the sample size is. So because this is not the central limit theorem type of problem, we don't actually have an N. So we don't need that for this particular value. You're just going to use your traditional z-score formula. So what does the $3.50 represent? Is that your z-score or is it your raw data value?
$3.50. It's the data value.
It is the data value. Yes. Yes. Your z-score is not going to have a $ sign attached to it. because your z-score is a standard score. So it doesn't have a unit. So in this case, your X is going to be $3.50. Now, also keep in mind, they want you to find the area for a peanut butter jar costing less than that value. So you have to find the z-score first, then you draw the curve, shade the region, and then use the table to figure out what that area is.
So the X is the 350. So once I plug all these in, then I draw my z-score.
Yes.
And then I'll be able to.
Yes, exactly. You draw the curve. Once you actually calculate that value, you'll plot it here. And then remember, it wants less than, so you shade the area to the left. And then you look it up on the table.
Okay. I'm good at, so I just put too much on my plate and I don't know what to bite, what to chew, and what to live because of this job. But I'll work, I don't have to work today, so I'll work as much on this and my test, and then I go in at 2 tomorrow. So I have that 12:30 to 2 period, part of the 2 period. So if I have any question, I'll hop in back. It's a struggle. I didn't realize that how hard it was gonna be when I did it.
No worries, no worries. It'll be worth it though, for sure. But yes, come join me tomorrow if you have any questions.
I will, yeah.
Awesome.
All right.
All right.
Thank you so much. Yep.
You're welcome. Bye.